Good morning, good afternoon, and good evening, depending on where in the world you're joining us from. Welcome to our expert webinar, Augmenting HPC Workflows with AI, Enhancing Simulation, Efficiency, and Workflow Automation, brought to you by our friends at Hewlett Packard Enterprise and NVIDIA. I'm Brian Mink, co-founder and president of Data Science Connect, the world's largest data and AI community. Today, we're excited to welcome hundreds of attendees from all over the world to discuss how AI is reshaping high-performance computing to meet the growing demands of complex simulations and data-heavy workloads. HPC is the engine behind critical innovations in industries like financial services, manufacturing, and chip design, but traditional infrastructures are hitting limits. That's where AI comes in. By embedding AI into HPC pipelines without relying solely on pre-trained foundational models, we can accelerate simulation runtimes, automate workflows, and unlock new efficiencies across sectors. We're excited to introduce today's speaker, Steve Heibein, Federal AI Chief Technologist at HPE, who will be digging into practical strategies for integrating AI into existing HPC systems, real-world use cases in high-level synthesis, HLS, FSI, and manufacturing, and forward-looking insights into how these technologies are converging. Now, before we hand the stage over to Steve, we have a brief welcome video from our partners at HPE and NVIDIA.
Unlock AI. Unlock the potential to do more, solve more, discover more. Hewlett Packard Enterprise and NVIDIA unlock the power of generative AI, combining HPE's enterprise-grade mastery with NVIDIA's revolutionary AI breakthroughs. We're co-developing and co-innovating to simplify the complexities of AI, making it easier and faster to deploy. Not only are we building and creating together, our combined solutions empower teams to do the same, scaling AI from individual data scientists to an enterprise-wide platform for innovation. With all these things coming together as one, organizations can deliver on AI-driven business outcomes faster, seeing results in weeks instead of years. Welcome to the new world of NVIDIA AI computing by HPE. It's time to unlock AI.
All right, and with that, I'm going to welcome Steve to the stage. And Steve, it's all yours.
Hey, thank you very much, Brian. I appreciate it, and I appreciate everybody who's here today. I hope you'll find the information I've got interesting. And one of the things we're running into, if you think about it, that to stay ahead, enterprises need to innovate, and they need to innovate faster. And with the combination of both what's going on in the AI world and what's been previously going on in the HPC world, it's a great time to be able to see this merging of the two. Right? You want to predict the future. You want to know what's going on. And that's perfect for when you start looking at some of the modeling and simulation. And you also want to unlock data faster with high performance computing. And then when you look at it from a standpoint of I'm going to make quick decisions, AI works out very well for that. What I want to do is, before we get too far into this, I want to sort of like go back a little bit and just make sure that we have a level setting for everybody's understanding. When you start looking at, what is artificial intelligence, what is machine learning, what is this? I want to use the Russian dolls analogy. If you sort of think of it, one inside the other. When you look at artificial intelligence, that's the term, that's the broad term that covers all this. And when we normally think of this, a lot of what goes on in there is really more a matter of it's like rules-based or expert systems. I'll use medical analogies for all three of these. So if you look at what we used to do during the 90s, right, before the AI winter, what we were able to do before we had GPUs is really not much but try and say, okay, how would a doctor walk through triage of a medicine, of an illness? And so what they would do is say, okay, first I take your temperature, I take your vitals, so on and so forth. Then, and you would go down a tree, in a decision tree, so to speak. And that's what we do. We interview an expert, we create a rule-based tree, and that would be AI back in those days. But when you look at what we're doing is we're expanding that quite a bit. Machine learning has changed a lot there. That's where what we do is we have the machine or the algorithm learn based on data. So it learns and gets smarter the more data it has. And so it uses statistical methods and feature extraction to try and understand what something is. An example of this would be we might take 1 million x-rays and some that have show lung cancer and some that don't. And then through that, the machine learning, the algorithm would pick up and understand, I now can understand what is difference in this film, this one person's chest, and a series of actually 1 million of these x-rays, and say, okay, I can now identify where cancer is located, identify the location, and point that out. And that's where machine learning comes in. Now, if you go to the next step of what's happening with that, you basically have now looking at deep learning. Deep learning is now where we're using neural networks to understand more about there. And that's the case where we're doing things like take COVID as an example. What we did with COVID is we used deep learning to try and understand more and more about what, the illness, who was getting it, what all of the symptoms that were, and all the confusion that had gone on pretty early with that. I'll actually show an even better example of deep learning and COVID in a couple slides, but you can see how the progression of each way. And deep learning is a specific method of machine learning. Machine learning is a specific method of artificial intelligence. But if you really get down to it, what's simply put, what can AI do, right? You sort of look at it and say, it can recognize things. What's this object? Who's this person, right? It can find anomalies, what's different, what has changed, and if you look at like your Ring camera, right? Many of you have Ring cameras, and what it can do is it says, as soon as something changes in the picture, I alert you. It's AI. Or I can recognize that, yes, those are my kids coming in the front door. There's also things like classification. It's sort of putting these things, so if I look at it, what is the same and where does this fit amongst a series of examples? Recommendation engines, we all know that, right? If you've gone on and done any shopping online, you have these recommendation engines that say, or music, you listen to this, you might be interested in this, or Netflix, same thing. Here are other ones that are similar to what you've been showing you like. And then there's filtering, where we use filtering in a lot of ways. Mostly it's to remove unwanted content or noise or signals. I'm in the federal space, and a lot of times what they try to do is if you look at even the radios and trying to take different wavelengths and remove them so that you can understand the part that you care about, filter it down to that. Prediction, forecasting, those are big items within here, because if you say, okay, based on all these other tax returns that I've seen, some of which had cheating and some didn't, I can predict, if you give me a new tax return, whether that fits into which category. I can predict that it's cheating or not. Optimization, we use that for routes. Many of the routing, I've got packages that have to go to different places, unlike the post office, which walks house to house. When you look at Amazon and others, they have to go and try to have the shortest route to try and catch all the different deliveries they need to do in that day. But then something changed. Gen AI came along, right? ChatGPT. And you look at that, it was 2 years ago, October, all of a sudden there was this new thing. We said, what is this? What is this? At that point, it got into the zeitgeist, all the social media and all the newspapers, and everybody got very excited about this. And there's a lot to be excited about. What happens with Gen AI is we're taking in a lot of data, a lot of body of knowledge. And what we're doing is we're looking at and finding patterns within that. So, you bring in, and it doesn't matter whether it's, conversations, text, genomes, chemicals, videos, etc. So it can be any variety. And then what we do is we look at that with transformers and a certain type of model neural networks that then we could do is say, find me those patterns so I can understand them. And based on this, if you ask me to generate something, I can now generate content with that. Hence the name generative AI. But when you look at it, the popular Gen AI use cases today are very simple, right? Virtual assistant, but they work in many ways. A virtual assistant, I can provide information, you can manage your schedule, I can control smart devices, right? Content creation, creating of images, videos, reports, proposals, RFPs, responses, etc. And then you look at chatbots, more for like this customer interaction, where what I want to do is I want to ask questions and try and walk you through to maybe fix the problem yourself, or lead generation, order tracking, and then things like code copilots, where what they're doing is helping you with development of software and coding and documenting the code, refactoring the code. For instance, there's a lot of agencies within the federal government that are using COBOL, and most of the COBOL programmers have retired, right? And so they aged out of the system. So now they're having this challenge where they have this COBOL software that has been able to do some function in the government, and now they're trying to refactor it and then redo it in a modern language. Now, traditional HPC, when you look at that as an alternative, right, what it is you're really doing a physics-based modeling and simulation. Sometimes we call it mod sim, but modeling and simulation. So I'm able to use physics-based. So when I do finite elements modeling or computational fluid dynamics, etc., these are based on physics. These are equations that we've been able to deduce over the millennium. And so, this is really a case where, as opposed to AI, which is probabilistic, right? I'm predicting if I'm doing something with language, I'm predicting the next letter, the next word, the next whatever. Here's the case where with HPC, high performance computing, it's physics-based, so it's mathematical in nature. We know what Euler's equation is. We know what Bernoulli's equation is. When you look at all these different, what it is we're applying this to whatever our science is along the way. So if you start looking at the combination of the two, what you have is on the left-hand side, artificial intelligence and statistics based, right? And then you got modeling and simulation with these equations is physics based. Well, how does this attack one problem? What happened with COVID is the US Department of Energy and their supercomputers that were built actually by HPE, with those supercomputers, what they were able to do is do artificial intelligence to say, let me narrow down the potential candidates to look at for what the shape of that COVID spike is, right? And so this way they could understand that the ACE2 receptor on there, what's that shape? But what they could do is they say, I guess it's something in this range, this range, this range, right? And so it took from what would have been an unlimited number of possible shapes, would have taken forever to simulate, right, and model with equations. So what they did is they said, take a look at this subset, the smaller subset. And then what we're able to do is go and use, the physics-based equations for trying to understand this. It's based on these shapes are really based on the proteins that are there. So we do know enough of that information to say, this is what it should look like. And so with modeling and simulation, we got the exact shape. And then what we're able to do is take that shape and provide that to the pharmaceutical companies. So this way, that part that required massive, massive supercomputing to do, the US government was able to do that and then hand off to the pharmaceutical companies for them to try and find something that would work with that ACE2 to actually bind with that ACE2 receptor. So how does this work in some of the other things? I mean, traditionally, weather, manufacturing, energy, those were all HPC or physics-based in nature, right? High-performance computing, modeling, and simulation. But what's happening now is we're doing the combination where we're using AI to enhance the outcome. To sometimes when you take weather, to make weather more accurate or to make it so it's hyper-localized, we're able to take the physics simulation and then using AI to understand the local characteristics and make it smaller in terms of, the more granular, so it talks about your neighborhood, your area, or be able to do the same thing when we look at storms, be able to say, okay, I don't need that level of detail except for during the path of the storm and do the prediction of the possibilities. Manufacturing, a lot of what we're doing there is also trying to develop what the shape might be using AI to quickly go through shape simulations. And then we do the physics along with that. And with energy, a lot of what's going on, if you look at our the system of distribution of power and electricity around, that really is a routing problem in many ways. And what we can do is use things, with AI to aid the actual physics there. Let me give you an example of a real world example. NVIDIA created NVIDIA Earth 2, they call it. And what it is it's a digital twin of the Earth. And in that digital twin, they use a combination of AI, visualization, and simulation to be able to represent what's going on and also to predict what they expect to be able to go on. So this way you could start seeing, hours in advance of what's going to happen. They can also do what if scenarios and things along that line. But that's a nice combination of the two. In other areas like manufacturing industry, some of the other machine learning use cases that double up, like I said, with those simulations, ModSim, is supply chain management, the predictive maintenance, being able to understand when something may fail based on its actual operational information, right? The vibration, the temperature, the workload, the amount of time at work, the duty cycle, etc. Failure and defect analysis after the fact. A lot of this, what we do is we try to say, okay, based on the probability, but we can also do based on the simulation, modeling simulation, to again give you a better view into what may have happened. Cost, quality management, price optimization, and even asset management. So you see all these different areas in which they can work together. Now, here's a very interesting example. If you look at NASA, what NASA was looking at, they used large language model to be able to actually say, I want to generate a part. What they did, if you look at where there's the screw holes at the top and there's also on the base, there's also mounting holes there. What they do is they say, okay, build me a part using this material that has this kind of load, this kind of torque, right, et cetera, torsion and everything that's on there. And it says, build me that part, optimize it, and using these materials. For instance, they actually 3D print these parts in either aluminum, stainless, or titanium. But the purpose for this is what they want to do is they want to be prepared for when they're out in space. They can't say, oh, ship me a replacement part. They're going to need to 3D print this thing, whether it's a space station out on the moon, Mars, etc. And so what they're doing is preparing for that. If you notice, the shapes are very interesting there. So these are shapes that, as a human, we probably wouldn't have come up with something that actually is very sophisticated. It would have been much flatter, at the top. That would have just been one flat piece across there, whatever thickness. But this way, what they're optimizing it, for those cases, I needed to work in, these loads, these temperatures, and the least amount of material there. So you can see also that's Ryan actually holding one of the mounts for one of the panels too. So when it comes down to it, what we need to have certain things, whether it's ModSim on the left, and you see, they want higher resolution, they want higher fidelity, they want larger data sets. And on AI and ML, they're looking for larger AI models and shrinking training windows. They want to do all this quicker and quicker and in larger data sets. And what they're doing is they're coming together and seeing that that's very similar technology that's needed for that. It's clusters, large scale clusters with accelerators in there. So what it is, the compute that's very purpose built, very dense optimized, right? Because you have a limited space. When you look at some of the supercomputers that we've delivered, they're basically the size of a basketball court, some of them, the world's largest ones that we've done. And so Interconnects, very high bandwidth, high speed, low latency, storage, faster and faster. You want it to both be quick to the data, but you want to be able to have a large, high throughput along with that. And so now you're talking about the scalability that's going to hundreds of petabytes of data that's associated with this. I mean, you won't be running into necessarily those size problems, but it's nice to know that those size problems have been solved so that if you're having a cluster of a couple racks of accelerated servers, you know that we've tried it out in the most extreme case so that yours is a case that's easier to solve. And then, of course, there's a software stack that goes along with this. So what's happened is there's a saying, skate to where a puck is headed. And so if you look at where AI has been going, it's been going to bigger and bigger clusters. And clusters are something that in supercomputing we've been doing for a long time. And with the combination of accelerators in these large clusters, really, this has become a supercomputing problem. And so when you think of skate to where the puck is headed, the puck hit Hewlett Packard Enterprise. It ran right into us. We're the #1 supercomputing company in the world, right? We have the #1, 2, and 3 fastest verified supercomputers in the world we built. We built 7 of the top 10, and we have 16 of the top 25 supercomputers in the world for energy efficiency. So when you look at that, and then you take NVIDIA, which is the undeniable #1 hardware vendor for AI, and you combine the goodness of NVIDIA's AI gravitas and HPE's prowess, what you have is you have a nice combination. We call this NVIDIA AI computing by HPE. And so what we've been doing is doing some co-developed solutions to work together to try and simplify these problems, right? I was talking about how big. Well, what we want to do is make sure this is available to everybody to be able to use, no matter what scale they are. So what we've been working on is turnkey private cloud, which I'll show you, AI services and training to make sure that you're staffed and knowledgeable what you need to do, or be able to provide that for you in services. These are AI optimized services, systems. There's enterprise grade controls over them because everybody needs to make sure they're secure. And that's what we do is we build them so that they're secure at the data, application, and user layers. And then whether it's inferencing, tuning, or training, and for those of you who aren't familiar with the term inference, if you think about it, generally what happens is I've got data, I train the model, and then what I do is I use this trained model to infer a result. So if the model I trained was to identify faces, right? After I've done training it, so if I take another picture and bring that in, I'm going to infer who that is or what that scene is, whatever it might be. So that's what inference is. Inference is really using that model as opposed to training that model. And then you have virtual systems, other things, process automation. These are kind of what we want to do with these tools. So if you look at it, what we've done is HPE and NVIDIA, and here you can see actually Jensen Huang, who's the founder, CEO, and president of NVIDIA, and Antonio Neri, who's the CEO and president of HPE, and also the executives from the Los Alamos National Lab of the U.S. Department of Energy, all here cutting the ribbon on a joint project that we did together. Here's a couple other joint projects that we did together, NVIDIA and HPE. And these are using the Grace Hopper 200 chips. And so what we built is the one I just showed you that was Venado, and that's 10 exaflops of single precision floating point AI performance. Not to be confused with HPC performance, which is always double precision, a 64-bit precision. Okay, but so 10, 20, 21 exaflops in these different systems. And you start thinking about, why do I need that much? That's so powerful. What can this be used for? And you start thinking about it, it's really to solve some of the world's most challenging problems. And so when you look at things like accelerating oil and gas exploration, again, what we're doing is using that combination of traditional, where we used to basically blast sound, and then from there be able to tell where the oil was. Well, it's tough. Every time you have to set up for that, we're using AI now to say, these are what we predict would be the better oil fields. So we're starting in a better place, and we're having to use less of the simulation, in combination, predicting extreme weather events, discovering precision, life-saving precision medicine, and other things of that sort. So you can see where we're able to take that power, those powerful systems, to be able to really make some breakthroughs. What we've been doing, though, is, it is based on hardware, right? We have hardware, software combination of what we're doing. And what we've done is Hewlett Packard Enterprise and NVIDIA combining, where we're using their GPUs and their network interconnects. And we're using, whether it's enterprise grade AI, so into the data center for those things that are very specialized application. There are specific applications within there. We're doing engineered systems, so we're giving it turnkey solutions. And then to the far right, that's where we get into the largest and biggest systems for answering those challenging questions that are out there. And then, of course, they got to be they got to be on a broad range of AI services, software platforms, data management, et cetera, that goes along with it in a hybrid environment. So let's talk about 3 paths to AI. First is, what you want to do is, if it's a specific application out there, there's a package out there. For instance, if I'm doing video surveillance, there's packages you literally can pull off the shelf, so to speak, and you can apply those. And these are packaged apps, very easy, no code development. It's configure and go. In the example I'm using here, it would be like, I've got so many cameras. I want to do so many things on there. What do I want to do? Identify stuff? Do I want to, the purpose and what I'm going to be using it for? So I know that. And then I can go and just configure how many servers, how many GPUs, and now I've got a solution. Then there's the AI appliance. What we've done is, working with NVIDIA, we built a turnkey solution, all in one platform, hardware, software, network, storage, everything that you need to run, all in a rack that we ship, all racked, cabled up, and bring to your site. On there we have what I call an opinionated software stack. It's a stack that we've co-developed between NVIDIA and HPE to be able to provide the types of tools we expect you're going to need. But we make sure that it's extensible, so if there's something else that you want to do or bring in models that are different, we make that available to you too. And then finally, there's the AI factory. It's when you start looking at something that I want to build something custom for my specific purpose, right? And what you want to do is you want to have it built for your outcomes, very large scale in nature. I'm going to double click on each one of these. So let's look at that AI applications. These are a case where there's this is just a few of the literally thousands of logos that are out there that can actually run on our systems. But what we've been doing is we work in combination with all these commercial applications, and NVIDIA has a exhausting about 1,800 different applications and tools in their catalog. And what we do is that taking those applications all work on the HPE platform, because what we do is we build NVIDIA certified platforms to make sure that we can work together on that. But there might be tools for data management or data analytics, visualization, surveillance, medical imagery. You can see some of the list of some of the different types and use cases for some of these apps. And then let's look at that AI appliance. And I'm going to do a double click here. Basically, what it is a turnkey generative AI platform. It's built for developing both Gen AI and ML and being able to do things like chatbots, et cetera. It's very quick startup. We got these solution accelerators and NVIDIA blueprints. And what they are is they're small small applications. Think of it like almost like minimally viable products for different use cases that you might be interested in. Like I said, software copilot, a chatbot, a variety of different things. So those are all pre-built in there to make sure that it's usable right away. It's one-day installation. Like I said, these things we bring in fully racked and stacked, labeled and cabled. And so when that comes in there, we have that up in one day. After you bring it from your loading dock to your data center floor, we'll have that up and actually show you how to do a RAG implementation of a large language model. For those who aren't familiar with RAG, think of it as retrieval augmented generation. It's a large language model that what we do is we retrieve your data, we augment that large language model so it answers using your information, and then it generates answers based on that. So what it is it allows you to specialize something. So if in your organization you have some knowledge base that you would like everybody to get access to, very simply using a chatbot, RAG would be a great way to do that. And so what we do is you have a 3-button way to actually implement a RAG large language model. It's basically you say, pick the model I want to use, right? Based on what my use case is. I then point to whatever my corpus of data, my body of knowledge, right? And then 3, I say, what's my user interface, for being able to show it to others and people to get access to it. So it's that simple. And then also, in addition to just that, there's a robust software stack and hardware stack to be able to do this. And this has been co-engineered by the two of us. Here's sort of an example of that stack. If you look at it, at the top, we've got all these models and partners, and the code that I was saying, the accelerators that we put in there, software accelerators, application accelerators we put in there. And then if you look, NVIDIA AI Enterprise software, what it is that's the goodness. In fact, if you think about it, Jensen Huang, I mentioned the CEO and president of NVIDIA, he said that NVIDIA software is the operating system of AI. And so what we did is we said every operating system needs some applications. So we built HPE AI Essentials on top of that to give it a GUI interface, to pull it all together, to make it very simple to take these components that come with that NVIDIA AI Enterprise, and on top of that, make it easy, similar to what I was talking about, that 3-button click, and then you have an application running. Also, of course, on the infrastructure side, NVIDIA's GPUs, world record-holding GPUs, and their NVIDIA Spectrum X networking, and we combine that with our HPE AI servers and our HPE file storage, and then on top of that, what we do is we have services from us. In fact, the way that works out is we do this as a white glove installation, and then you have a week of support after that for if something else comes up, you say, I need to connect it to this database, this data source, this whatever. The whole key is what we try to make sure that this is almost a guaranteed success for you. On the right-hand side, what we have is using HPE's private cloud control plane. What we do is we give a cloud-like experience. And so all the things that you're expecting from administration and support, right, is built in there. So whether it's setup, inventory, asset management, workload provisioning, orchestration, or it got things like VMs, runtimes, or Kubernetes containers and cluster management. All of that's in there, plus the monitoring, observability, and security that you're expecting. And with the security, as I mentioned earlier, it's secure at the data, application, and user layer. Now you take all of that, and you can see under there in the purple boxes, it's basically developer system, small, medium, large, and extra large. So if you take the 4 to the right, think of them as t-shirt sizes. So what you can do is have them in a t-shirt size configuration. And then the HPE GreenLake Cloud, we call that the cloud that comes to you. So this is built so it's an on-prem architecture for you, so that you have the sovereignty and control of things that you need. Now I'm going to take a look at the hardware for this. With the hardware, what you've got is small, medium, large, extra large. And those are like those t-shirt size I said. But in addition to it, if you'll notice, it's 4 or 8 GPUs. And if you look at medium is 8 or 16 and large is, so you look at, they double. It's almost like saying, I've got a t-shirt and I've also can get it in a large size, so it's almost like small, long, medium, long, and large, long. And so with those, we've been shipping those for over a year now, about a year now at this point. We are going to be adding an extra large coming up. And part of it is we want to roll over to the Blackwell GPUs. So we're moving from the Hopper GPUs over to the Blackwell, and that'll be the first one moving over there. And we expect all of these to progress along the way. The one I didn't mention until just now is the developer system. So if you sort of think what goes on with the developer system, that's really set up to be able to start fast. What I want to do is I want to be able to start developing, and it has all the software that's on the small, medium, large, and extra large is available on the developer system, except what you don't get is in those t-shirt size ones, you'll notice there's a lot of actual servers within there. That's because we have 3 servers to be able to do the Kubernetes for the cluster management, the login. And so this way, what you have is no single point of failure when it's coming there. You want to have full availability. We have GPUs in 2 different servers. So again, the same thing. So this way, you have a reliable system. The developer system says, okay, that's kind of that's your responsibility. What we're going to give you is something that you'll be able to develop on that software suite for then deployment when you know how big your application is on a large or extra large. Now, going to the far right, well, if you want to scale fast, so you can see how we go start fast or scale fast. So we're making that all available. So the next thing to look at, if you look at the AI factory, this is what we're doing is we're going to build and deploy AI at scale. So you talk about larger applications. And like I said, that'll start from something that could be 16 GPUs to 16,000 GPUs. So the range is quite large. And so with that, large scale clusters built up from high performance accelerators, GPUs from NVIDIA, high performance networking, the Spectrum X, network connections from NVIDIA, high performance storage from HPE, custom driven software stack, because we know that when you're building an AI factory, you may have already an opinionated stack of your own. And what we can do is work with that. Or what we have is we have another stack, software stack we can help you with. But usually factories are built very bespoke, very custom for each case. And then what we do is they can be liquid cooling or air cooling. And that's one thing I'll talk about in a little bit, how you're finding that as these GPUs get hungrier and hungrier for power, they also have to be cooled. So a 1,000-watt GPU needs 1,000 watts of cooling. So you're going to find that these systems are moving more from an air-cooled like environment in a data center to liquid cooling and liquid cooled data centers. And then they can be built on-prem, in a colo, or as a service. And so you can just see where this is all headed. Now let's talk about the AI factory concept. Basically, to think of it, every factory has raw materials, right? My data, my algorithms, my AI infrastructure, right? And then what we're doing is we got composable blueprints. This is where we say, if I put this together this way, these AI infrastructure, these algorithms, along with the data, this is how I can create something of value. And something of value would be AI applications and actionable insights. So what we've done is to try to make this thing for the AI factory, it's repeatable, scalable, resilient, and secure. And when we talk about those composable blueprints, they're based on the tens of thousands of clusters that HPE and NVIDIA have built. And so what it is it's based on the results of a knowledge that we've gained over all of this time. So other factors or other characteristics of a AI factory is we believe it needs to be multi-tenant. And so secure multi-tenancy, dynamic provisioning. And so what happens is we want to be able to provide GPUs as a service as people need them. Self-service in nature, and and have compatibility. So in some cases, we're actually building these for a tenant who has subtenants. So what we can do is make this for if you're going to be charging back, doing chargeback and such. So we'll have automated resource monitoring and billing. So you can do either chargeback, showback, etc. And then having a central control and observability across all of these resources. And then finally, we need, to what you want to do is you want to do that, provide that value-added services that might be needed, specialized apps, other support that goes along with this. Now, what this takes is components like I mentioned, whether it's compute, the Grace compute chip, right, from ARM chip from NVIDIA, or Hopper or Blackwell as we move to for the GPUs, and then networking, storage, etc. So these are the main components we're doing. NVIDIA AI Computing by HPE, what we've been doing is working to make sure that we have these time to market with every one of these new steps that NVIDIA comes out with a new architecture, a new CPU, GPU. What we're doing is we're going stepwise with them with different products, whether it's the GB200 NVL72, the HPE ProLiant XD line, and those are the ones that are built based on the DGX standard for configuration, etc. That's where you have 2 CPUs and 8 GPUs that are all NVLink together. So you have that interconnect between there. The ProLiant DL380A, we can actually fit in, of those double wide GPUs, we can fit up to 10 double wide GPUs in there to work together to solve a problem. In fact, we use that box a lot when we're doing things with Omniverse. Omniverse is the digital twin software from NVIDIA. And then on the right, that's our Grace Hopper and Grace Blackwell systems is what we have on the right-hand side, the Gen 12 version of that. I mentioned earlier about heat, right? One thing that's happened is the temperature, the T case, right? The temperature that they want on the top of that CPU or GPU is going down. They want it to be cooler and cooler and cooler. Why is that? Because now a lot of these chips are multi-layer chips. So what will happen is you might have 3-4 layers of actual silicon within that one enclosure, that one, what to you looks like a chip is actually a series of different layers within there. And so what you need to do is you need to make sure that's cool enough so that you can keep the first, second, and third layer cool, not just the fourth layer up top. So that's coming down. And then you look at the power of CPUs is increasing over time, but GPUs even faster. So what you're talking about is GPUs at maybe 1,000 watts. And so imagine it's like taking 100, sort of 10 light bulbs, 100-watt light bulbs, right? Traditional, not LED. And so what you would get is the heat that comes off of there. Well, a typical data center, might be something that be as low as 10 kilowatts per rack is what I might have an allocation for older ones. For more modern ones, they're going to be 25, 35, maybe 50 kilowatt is the amount of power and cooling that they've allocated per rack within a data center. So you can imagine if I've got a system, a server, that's going to be someplace around 12 to 15 kilowatts, and I've got a rack that can only hold 50, I can only fit two, 3, or 4 of them in that range. And so what it is, I need to be able to cool that. And if people want to say, I want to have much more density within there, you now have to go with liquid cooling. So it's become that air cooling alone is not sustainable. So you're going to find that most modern data centers or data centers you're going to need to move into, if you're doing AI and HPC, are going to require liquid cooling. So how do I get there from here, right? Well, at the top, you can see I can retrofit my data center. If I got an air-cooled data center, and there's ways to do that. A lot of times that's an impractical thing to do, either a footprint, other physical challenges that might be there. Another choice is go to a new data center, build or buy a new data center. Those are possibilities that are out there. But really, we're finding a lot more people are saying, I'm going to colo with existing liquid-cooled data centers. So I could be maybe something like a Digital Realty, Equinix, Hydria, Qscale, IQT, those servers, those data centers, vendors, those colo vendors, all have ones that they'll offer with cooling already in it, liquid cooling in there. And then you could go say, well, I want to move instead. I've got a workload. The HPE AI Cloud, we actually support that. And ours are all liquid cooled. They're 100% renewable energy that we use for it. And in fact, in some of our data centers, we actually take the heat, the waste heat from that, and pump it in for use of either heating the adjacent buildings, or in one case, for agriculture. And what we're doing is do it for agriculture, to heating it up. So this way in the wintertime, the buildings there are all warm. And then finally, one thing that we've been doing for years, for decades actually, is the modular data center. And so HPE, we right now have over 300 patents in liquid cooling, and our history goes back 30 years. But let me show you the one thing I wanted to show regarding that. For those people who don't have the space, don't have the thing, they don't want to, they can't really retrofit their data center. What we've done is what we call the modular performance optimized data center. And so the mod pod. And here's a case where what we did is, this is a system that we built for this is actually in England. And it is NVIDIA GPUs inside HPE servers. And what we did is we were able to bring this on site and drop that in there. And from a standpoint of what we were able to do is cut down the development of a new data center, which is generally about 3 years, bring it down to under 9 months for the entire process between pouring the slab, running the power there and everything else, and then us dropping in the data center and then populating with servers. And what it is these aren't these shipping containers that people used to do. These are actually built off of, again, we have a series of formats that we can do to build this to handle whatever your workload is. And while the components are modular, the shapes and sizes we can do are pretty unlimited to be able to support whatever restrictions that you have. We have some people that are taking these in very harsh environments. They'll be sitting outside and running there fine. But if they're very harsh environments, they actually put them inside a warehouse. And then they're able to bring this up very quickly inside there without any of the environmental constraints. So this was a lot of information. I really appreciate that you sat through all of this. But what it is, if I can get anything across, it's obvious that you can see where HPC, AI, they're merging together to answer the questions easier, more thoroughly, with greater detail. And so what we're able to do between NVIDIA, HPE, is provide AI from edge to exascale, in a hybrid data formation where whether we're working in conjunction with what's in the cloud or on-prem or multi-prem. And what we do is we put a cloud-like experience, a user interface on top of this to make it easy so that the transition and all of the things that you want about the public cloud, we can give you on a private on-premises cloud experience there. And then all of this with our enterprise-grade support. We have support we actually operate in over 50 countries around the globe. And so I appreciate your time. I hope this was valuable to you. And what I'm going to do is, Brian, I'm going to like to turn this over to you at this time.
Thanks, Steve. Excellent presentation. Lots of great insights for our audience. Thank you all for joining us today. If you missed anything and would like to rewatch any of this webinar, you can refresh this page just a few minutes after the webinar concludes, and the video will be available here. We'll also send it out tomorrow via a link to our YouTube channel. I want to say a special thank you again to Steve for the great content, and to our partners at HPE and NVIDIA for making this webinar possible. And we'll see you all again next time. Thanks.
Thank you.
Thanks, Steve.